my joy and privilege to introduce this next session entitled Quadrivium in the Age of STEM. And your presenter is Dr. Karl Heine, who is an assistant professor of mechanical engineering at Embry-Riddle Aeronautical University in Prescott, Arizona. He currently serves on the church council of Shepherd of the Hills Lutheran Church in Prescott, Arizona. And I might also mention that he's the son of Melinda and also fond memory Bill Heine, Reverend Bill Heine. So let's welcome to the podium Dr. Karl Heine.
Good afternoon, everyone. Hopefully you can hear me okay. It's a real honor and privilege to be able to speak to this audience. This is something I am very passionate about, and I'm glad there's some interest out there as well. So to begin, I gotta admit a little bit of hyperbole in my abstract. I kind of introduce it with this idea that we've struggled to define the quadrivium in the contemporary era of STEM. And that's one of those broad sweeping claims to make it sound like I'm the only person out there talking about it, when in fact, we've had at least five that I counted, presentations on the quadrivium so far in this conference, and several more. So I should commend CCLE for all of the interest in discussing what the quadrivium really means today. I really hope that my small contribution here in this presentation is helpful towards that end. I'm going to provide this afternoon a philosophical and practical contrast between two pedagogical frameworks, STEM and the quadrivium. And you may balk, as others have done, that there is actually any competition between these two. Why don't we just embrace STEM and teach it better than public schools? So in order to answer that, I actually really need to define STEM. And I'm going to tackle this presentation through two main theses. One is that nothing is neutral, and that includes STEM. And two, that the Lutheran quadrivium provides a superior education for service to our neighbors and citizenship, particularly in the kingdom of the left. Here's our general outline. We're going to tackle STEM, and then we'll talk classical and quadrivium. So let's jump into it. We all know what STEM is. Here's a cool figure from I stole that from Houston Independent School District website. Thank you to them. But let's create a little, begin this discussion by looking at what some other people who are interested in classical education, more broadly, say about STEM. In a 2017 post or article on the Imaginative Conservative, an individual by the name of Dr. Howard Merkin wrote the following: trying to put science in a classical paradigm is putting new wine into old wineskins. Jesus warned against this while talking about religion, but it works for science also. Modern science just does not easily fit into a classical paradigm. While Great Books College might try teaching science using a historical approach, advanced STEM is not taught like that in rigorous university programs. He argues in that same article that the quadrivium is obsolete. He further states, or rather implies, that we should throw off the shackles, my words, of Dorothy Sayers and Douglas Wilson and their humanities-focused approaches to classical education. And instead, we should teach and embrace STEM. Isn't he at least partially correct? I mean, modern science really doesn't fit neatly into a quadrivium or classical paradigm. And historical approach is quite difficult for teaching STEM, especially since many original sources for these modern scientific concepts are rife with errors. So as you go and use an ad fontes approach, you have to deal with the errors that they made in their initial assumptions. The science is, of course, developed. So, and also an advanced STEM is certainly not taught at universities. I can only speak for engineering, but we don't teach from a classical approach at Embry-Riddle, although I do actually attempt to include some elements in my particular classes. So if we claim that a classical education is the best for inculcating our students with good, true, and beautiful, that it conveys the good elements of cultures to future generations and prepares those students to serve their neighbors in any field, including science and engineering, then why shouldn't we fully embrace STEM? Teach it from a Christian perspective. We can certainly do better than our pagan counterparts. But to do this, we need to know what we're talking about. What is STEM? Okay, science, technology, engineering, math. We got that. We also know that it generally refers to K through 12 education. I can assure you that engineering programs don't talk about how they fit into the STEM education field. That acronym is generally applied to K through 12. But who owns the terms? Who owns what STEM means? What's meant by each topic? To get an answer to this, I suggest we look at state curriculum standards. STEM is an acronym of contemporary education writ large. So unless we go and actively redefine it, we are sort of subject to the definition as it sits out there. And the place where it's defined are in state standards, because that's what your textbooks will be written to meet if you were to go buy something off the shelf and then use it. And so even if we reject these non-religious biases in the standards, the vast majority of the available STEM curriculum will use the definitions that we're going to proceed through today. I'm going to use Arizona Department of Education as my example because that's where I live currently, but I believe this reflects quite closely most states. We begin with a working definition. This is the first figure that shows up on the slides when you look up the Arizona Education Science Resources, and it tells us that STEM paradigm provides hands-on and relevant learning experiences. It equips students with critical thinking, problem solving, collaborative skills, establishes connections between a workplace, community, global economy, and it helps students develop a conceptual understanding of math and science concepts, teaching technical and engineering practices, and disciplinary discourse. I submit to you that this is not particularly helpful. In fact, it begins to illustrate actually my first problem with STEM, and that is STEM in general is incoherent. We did not read a definition anywhere up there. We got a list of attributes and discussion about science in EduSpeak, but we didn't get a definition, and this problem we'll see more and more. Science, technology, and engineering and math are certainly related fields, right? But they don't really lack any unifying principle, just the terms themselves. Sure, math is used in science, technology, and engineering, but it's also important in personal finance, commerce, logistics, business administration. So it's not a comprehensive list. It's also, in the sense of not being comprehensive, the topics are interrelated, but those connections are not strictly required. For example, what technology is required to perform engineering? A slide rule, a four-function calculator, graphing calculator, a high-performance computer running ANSYS Fluent finite element software? None of the above? What exactly results in a complete science or STEM education? There's nothing here that tells us what that is. So we're going to have to dive further in. So let's begin with science. What's meant by science? Well, from the Arizona Science Standards, last updated in 2018 in the introduction, I found what looked as close to me as I could find for a definition, which is scientific thinking enables Arizona students to strengthen skills that people use every day. Solving problems creatively, thinking critically, working cooperatively in teams, using technology effectively, and valuing lifelong learning. A fundamental goal of science education is to help students determine how the world works and make sense of the phenomena in the natural world. Again, we're given a very ambivalent definition that's really just a list of skills that are not unique to science at all. A fundamental goal is given to us, but we're left wondering what other goals are fundamental. Is that it, or are there more? Let's keep digging. So we're going to dive into now the dimensions of science. This is all in the same document, so at least you can find it all in the introduction together. And what we learn is that science is built around core ideas, 3 of them, cross-cutting concepts, good EduSpeak, and science and engineering practices. All right, you can attempt to decipher this figure at your leisure. I submit to you that it is, again, a representation of this incoherence, because what exactly about physical life and earth and space make them the pillars upon which all science is founded? Well, let's go in and see what is actually meant by core ideas. So here we have the learning outcomes that Arizona uses when they talk about the core ideas of science. And these come from working with big ideas in science education, which is something that has been adopted by a variety of states. So this, again, is not unique. What we learn is that earth and space science actually means the religion of anthropogenic climate change. What life science actually means is the mythology of evolution. Furthermore, we find that life is in competition. We have a zero-sum view of all the resources that God, well, they'd reject God, of course, but that God has given us, which places humanity in conflict with the world in which we live. It may be possible to take a science textbook off the shelf that's been written to meet state education standards and go through it and eliminate the evolution and eliminate the references to climate change, but this is like living in a house while removing its foundation. Or in a sciencey manner, you might think of it as in computer coding. If you've ever had a chance to do that, would you rather write your own script or would you rather debug a broken script written by somebody else? Right? There's a lot more work involved on the left-hand, well, my left-hand side, you're right. All right, so springing from this bad foundation, this rotten foundation, the bad stuff is actually taught as advertised. This is sort of a corollary to that, but let's look at the science and engineering practices. So that was that outer ring. The description of this is, for decades, teachers have utilized the scientific method as a methodology. It's a method that is a methodology. Anyway, sorry, a scientific method that's a methodology to engage in scientific inquiry. Traditional implementation has resulted in viewing science as a linear process. The new vision calls for students to engage in multifaceted science and engineering practices in more complex, relevant, and authentic ways. In other words, students are not to learn a systematic approach to investigating a phenomenon. No, they are to engage with it in an authentic manner. This is simply foolish. People have interacted authentically with fire for millennia. But it took very disciplined investigation using the linear scientific method for us to end up today with what we know as the heat engine. And if that's a new term for you, happens to be the class I teach about, it means anything that converts heat into motion, from heat to motion, right? So your automobile is a heat engine. The power plant, the natural gas power plant in Lincoln is built around a heat engine, and that's how we have electricity, and we're running this projector right now, right? All of that happens through a very disciplined approach to the scientific method, which STEM rejects. What you end up by teaching this nonlinear approach to investigating the physical world is undisciplined minds that can't think linearly. All right, we've got science and engineering kind of covered there, so let's talk technology. The Arizona Technological Standards present a vision of what it means to be technologically literate, informed digital citizen who is college and career ready. Today's students must be prepared to thrive in a constantly evolving technological landscape. The Arizona Educational Technology Standards are designed to empower student voices and to ensure learning is a student-driven process. So I'll leave aside that last one for now, and we'll just focus on their objectives. We heard a lot about aims of education, and so you can maybe see where I'm going here. The objectives are wrong. The first one, technological literacy, to figure out what that means, we go to a 19-page example document. It's not prescriptive, it's just an example that they give that lists all sorts of things associated to using and manipulating computers, printers, going on the internet, things like that. And you end up with an educational standard built around using shortcuts to operate a computer, right? This is trivial. Suffice it to say that, like, the vast majority of this is trivial. People learned how to use the basics of computers as adults, as the personal computer was developed, without 13 to 17 years of indoctrination. So I say it's like padding stats because the schools can set these up and then immediately succeed with very little instruction. I mean, certainly you can go in and find some more advanced things, but the vast majority of it, you can get all proficients, right? So that's a trivial objective, and we would sort of reject that as being not worth our time. An informed digital citizen, though, is much worse. First off, we recognize it as globalist language, because citizenship is now disassociated from the country. Dissociated? I don't know. And furthermore, as inheritors of Western civilization, we recognize that digital citizenship is not citizenship at all. It's dehumanizing. It's moved you into an avatar. You're no longer a human being who's a citizen. You're just a persona online. So we reject that as well outright. And then finally, college and career ready. I believe we actually heard about that this morning here in our plenary, and we've heard about that before, but our goal is not to make students who are prepared to go get terminal degrees and have that credential on their walls, or to go get high-paying STEM jobs. Those are fine, but they're not our aim. So this brings us to my penultimate criticism, which we find in mathematics. So we got STEM, that's what I'm going through here. And so in mathematics, what I really want to focus on is that even the good things that we find in STEM aren't done well. The good stuff isn't taught as advertised. Here's some stuff, if you will, I won't read it all, about integrating technology into mathematics. And the line that I want to highlight here is that technology should not be used as a replacement for basic understandings. Absolutely. We fully agree with that. But it may surprise you, or maybe it doesn't surprise you, that I teach junior and senior level engineering students who cannot pass a test. They cannot function mathematically without a calculator. I even have, I would call that a significant minority who fit in that category. And then a small minority, a few individuals, I have students who can't function without their calculator. Suffice it to say that after 12 or 13 years or so of STEM education, they are not technologically literate, and they have no mathematical understanding, or insufficient mathematical understanding, right? So even though the standard tells us we're going to do this, it doesn't end up being taught as advertised. So let's summarize what I've said so far in kind of the order I presented it. STEM is incoherent, it's got a rotten foundation. The bad aspects of STEM coming from that foundation are indeed taught as advertised. STEM has the wrong objectives, and the good stuff isn't taught as it's claimed. All right, at this point, you might go back to Dr. Merkin's quote and say, hey, we can fix all that. We could simply teach STEM from a Christian perspective, and we could do a better job demanding excellence and getting rid of this reliance on technology. After all, math is objective. Right? Well, I submit to you that math is objective in the same way that English is objective. Math is simply a language, and that language may be used to convey truth or convey falsehood. My final critique of STEM is that it trains us to view things that are conveyed with math as being true in and of themselves, because the math was good. But it neglects the fact that we don't actually use math for its own sake. We use math as a tool. When someone presents say a statistical analysis with a 95% confidence interval and all the math looks good, we end up taking their conclusion as sound because their math was sound. But if the underlying data doesn't follow a normal distribution, their final conclusions are bunk. And so what we find ourselves is, in modeling parlance, you might get garbage in equals garbage out, or if nefarious purposes are at play, you might say, figures don't lie, but liars figure. As Christians, we recognize that we must be vigilant, so that we are not taken captive by hollow and deceptive philosophy, which depend on human tradition and the basic principles of this world rather than on Christ. We must never assume that any subject is neutral, for there is no such thing. Now, I have a little bit cleaner way of rewriting this that I added. And so here we might look at the problems of STEM rephrased in a little bit more logical order. It's got a rotten foundation, it's got bad objectives, it's incoherent, it isn't taught well, it produces unwanted outcomes, and there's the Colossians 2:8 verse for you. So, if we reject STEM, then what? Well, obviously, I'm going to tell you a classical approach, right? That's what we're here about. And we would start, if we would go back, we would start and look at, say, Plato's Republic, where we have the discourse between Socrates and Glaucon, where he presents an educational scope and sequence, if you will, for training good rulers. And in that approach, we get what we would summarize as a description of arithmetic, followed by plane geometry, followed by solid geometry, followed by astronomy, followed by music. And somewhere above that is the study of theology. Well, as we also learned this morning, the theology is not the ultimate goal of our study. No, the theology is the foundation of our study. So we would place the theology not just as at the top, of course we would put it there, but also throughout and also at the foundation. And so of course we're not going to just take Plato because that's classical and all things classical are good. No, we're going to rearrange that. And we're going to look at it a little bit over history. If we want a Christian interpretation, also minor point, he's got 5 subjects. We get 4 subjects of the Quadrivium when we get to Boethius, so we got to wait 900 years to get to the Quadrivium. But let's at least look at a Christian perspective on Quadrivium. And here we have Cassiodorus telling us that mathematics is a science that we call in Latin theoretical, since it considers quantities in the abstract. We define as abstract the quantity that is separated mentally from matter or other accidents, for example, equal and unequal, or other things of this sort, treated by reasoning alone. And then he defines, arithmetic as the study of quantity, that which can be counted in itself. Music is the study that discusses numbers that have a relationship to those that are found in tones. Geometry is the study of stationary magnitudes and shape. Astronomy is the study of movements of the stars in heaven. As we can see here, the classical approach is to teach the language of mathematics in an organized, logical manner so that students learn not a bunch of formula or processes, but rather so that they learn to think in the abstract. This is a timeless goal that doesn't depend at all on the late literacy in the latest scientific technologies or knowledge of current engineering practices. No, under a classical paradigm, the subjects of science the development of technology, the application of engineering lie in the domain of natural philosophy, for which the Quadrivium is preparatory. You may question how this approach is particularly superior. After all, those definitions by Cassiodorus don't translate well to modern curriculum. How exactly is astronomy the precursor to the study of thermal power cycles? What does the study of tones have to do with chemistry? So to show its superiority, I must at least show that the Quadrivium has a solid foundation, has the correct objectives, is coherent, and teaches good things well. Of course, we'll do this from a Lutheran perspective. These are in contrast with all my criticisms of STEM. I think there's an organization out here involved with that. I stole their logo, and I think the CCLE is on board with trying to do these sorts of things, particularly from the Lutheran approach. So let's start. A proper foundation. Why study STEM at all? Why study the Quadrivium at all? What exactly is the value of a good math or science education? The theme of this conference, I think, gives us the answer. The only real value in studying a bunch of technical subjects is to help us fulfill the second table of the law, to serve our neighbor. Knowing the Quadrivium and applying it to study natural philosophy can help us learn about our Creator through our understanding of the created world. But they do not lead us out of Plato's cave into the light of truth. No, the only truth, the revealed word of God, which is true, can release us from the bondage to sin and set us free in Christ. With perhaps the small exception of being able to count the number of years in the genealogies of Genesis 11, I submit to you that math is pretty unnecessary to read, mark, learn, and inwardly digest the scriptures. And so we, especially as Lutherans with our proper understanding of vocation, should study the quadrivial arts not to lead us to salvation, but for their use in the kingdom of the left. We ought to train our God-given talents and develop our mental faculties to fulfill God's command. God's commands through Scripture. We might start with one of his first given to mankind in Genesis 1:27. So God created man in his own image. In the image of God he created him, male and female he created them. And God blessed them and said to them, "Be fruitful and multiply. Fill the earth and subdue it, and have dominion over the fishes of the sea and over the birds of the heavens and every living thing that moves on the earth." In order to exert dominion over the natural world, we must have knowledge of natural philosophy, again, for which the quadrivial arts prepare us. We're also citizens in this technical age, and in order to participate in society, we need to be able to serve our neighbors in the temporal world by engaging in commerce, by building things, by maintaining infrastructure. And just as Plato was interested in training good rulers, we should also train our children to become, or at least have the potential or the background in order to become experts in leaders in their particular fields. If we don't, you end up with all of your science, your experts in science, being models of Anthony Fauci. You end up with your technology being developed by transhumanists who reject having children because they are leading the next level of evolution by producing AI. You'll end up with your engineering done by people who would gladly let you die in the dark in order for them to make a token, insignificant, or perhaps not even real reduction in the amount of CO2 in the atmosphere. And your math will be performed by intellectuals who seek their own intellectual prowess and do very difficult computations that serve no practical purpose. The Lutheran foundation on the six chief parts, or more thoroughly, the symbols of the Christian faith, including the creeds in the Book of Concord, provide us the requisite origin for developing the contemporary quadrivium. From the Holy Writ and a clear purpose or objective to our training, we need a coherent program of study. This requires an inductive look at those ancient subjects. Okay, we're going to look at the specific subjects and extract from them the general principle that we really wish to teach. And I have not, you've seen this before, I believe even Pastor Kane said the same thing in his presentation. I first heard this from a video recording presentation by Dr. Veith, so wherever he got it, he's my source. But this is brilliant. Arithmetic is the study of number. Geometry is the study of number in space. Music is really the study of number in time. And astronomy is the study of number in space and time simultaneously. The arts themselves are clearly interrelated and logically progressive. They're also parallel. One can and should study advanced arithmetic even after learning the fundamentals of music. This will become clear in the next few slides because we'll start to map modern math subjects to this quadrivium. Right? We need to do a little bit more precise explanation here. However, note that the quadrivium does not require any specific mathematical skill or specific knowledge in contemporary engineering practice. Instead, it requires a fluency in a language, the language of mathematics as applied to the four dimensions in which we live, the three dimensions of space and time. Let's dive a little bit further into what each of these might mean today. What's meant by arithmetic, or the study of number? Well, certainly everything we think of in good old-fashioned elementary school arithmetic, right? We got counting, four basic operations, fractions and decimals, accounting or dealing with money, right? But it means more. Arithmetic is not just a simple subject for elementary school children. It involves concepts of algebra, concepts of functions. Thank you for modern notation. We can thank Leonard Euler for that, who was at least a devout Christian. Series, statistics, number theory, which might be extremely complicated, esoteric subject, or basic number theory of ordinal versus cardinal numbers, prime, perfect numbers, rational, irrational. There are many levels of study for which arithmetic applies. We move logically from a concrete to the abstract and from the simple to complex, but throughout they're all useful. And we can begin our investigation of the natural world, the study of natural philosophy, right away with young children, using the tools of arithmetic. What about geometry, or the study of number and space? I bet you can guess at least one of these. Okay, all right, so measurements, ratio and proportion, coordinate systems, and plane and solid geometry, of course. Trigonometry fits here. And you might make an argument that linear algebra could be placed in this category. It could also fit very nicely in with arithmetic. But I submit to you that it's actually relatively easy for us to map these modern mathematical subjects onto this Quadrivium framework, because this Quadrivium framework is simply explaining a language. So all we have to do is tie all these disparate subjects to a common language, or common reference frame. Oh man, my animation's messed up, sorry. So study of number and time. What is meant by music? Of course, counting time, I submit to you, reading and singing good music is a sort of a gymnastic corollary. We're going to train our bodies in music as well as training our minds in music. Business math, things like net present value, time value of money, discount rates, interest, etc. Oscillating functions, we can get pretty complicated here. Just think sines and cosines, they can get nasty quickly. And of course, any sort of temporal data analysis, which we can do, of course, as PhD theses, or we can do in elementary science classes where they observe and make records of various data over a period of time and then go back and look at it. Right? So these concepts, again, are very broad and have many different levels. Because we're Lutherans, I wanted to make a special, take a little bit of time here, especially to talk about music and why we sing, basically. I guess I don't need to tell you that, we all know this. But we're Lutherans, so we would emphasize this point in particular if we want to make this very uniquely Lutheran. And it's good to sing, right? We're admonished to do so. So let the word of Christ dwell in you richly, teaching and admonishing one another in all wisdom, singing psalms, hymns, spiritual songs with thankfulness in your hearts to God. Because we're admonished to do so, we recognize that we should do so well. So let's train it, let's teach it. Another value of singing itself is that it helps organize our minds. And so if we're going to sing, let's sing things that are good and sing things that are instructive, rather than catchy tunes with vapid cliches. Every student should be trained to sing, but additional music instruction is valuable, of course, towards training accompanists. Again, sort of another gymnastic corollary, training your body to make music with an instrument. And that sort of wraps up music. This leaves us with astronomy. Astronomy is the study of number in space and time. And today I'm going to tell you that the language of number in space and time is calculus. Now, I'm a little biased because I teach engineering, right? Everybody needs to go calculus, of course. No, I mean, I do say that, but not just because I want to promote engineers. Calculus is the mathematical tool developed over the past several centuries to describe number in space and time, and it's foundational to modern interpretations of natural philosophy. Additionally, it teaches a different way of thinking about numbers, and it's actually things that aren't covered in, say, algebra. It's fairly philosophical, because you're pondering and rather applying things like instantaneous change and infinite sums of infinitesimally small bits. This is like Zeno's paradox comes to mind right away. But standing on the shoulders of giants, many of whom are Christian products of the Reformation and the Renaissance, who have developed the language of calculus, we can now actually harness and abstract those philosophical concepts, and we can apply them in practical everyday service to our neighbor. So I submit to you that a complete quadrivial instruction, we need to at least teach the language of differential and integral calculus so that students know what it is. What I am not saying is you need to be able to solve the heat diffusion equation, right? What you do need to be able to do is recognize what is being said by that equation. Solving this could be very difficult. So that's not what we're after. What we're after is literacy in the language of number in space and time. Calculus is also foundational to other math subjects. You study, say, probability and statistics, and you give me a confidence interval. Sorry, you just used somebody else's table of an integration function. Okay? It's foundational, it's built in there, and maybe you don't see it on the surface, but we, in order to say we give a complete education, at least have to give our students literacy in what this means. They don't have to have all the tools to solve all these problems, but they need to know the language. And then, as I've already said, it's foundational to all of natural philosophy. You can't go into a science field without some calculus, right? Again, you don't need super advanced calculus, but you got to know the language. So I submit to you that the culmination of the Quadrivium is indeed a first course in calculus. Here's a summary of the basic mapping that I presented earlier in table form, if you want it. Before I wrap up, let me tell you what I haven't said today. What I haven't said is, don't teach science. In fact, if I did say that, I believe the CCLE board would come throw me off the stage, because the marks of a classical Lutheran school involve the teaching of science, Mark 2.2.2. What I have told you is that you should reject STEM as a paradigm. It's not neutral, it brings a lot of baggage with it, and it's not good. Instead, we should embrace and further develop a Lutheran quadrivial understanding. A few parting thoughts. We should, of course, further define and refine what I've said about the quadrivium. So we can't just leave it as the 4, number, arithmetic is the number study of number, or music is the study of number and time. We need to give specifics. We need to map specific, maybe accreditation requirements onto this paradigm so that Lutheran schools can readily adopt it and map out the scope and sequence. And so I freely admit I have not done so, and I think it's worth our effort. We should also strive to write our own textbooks. I mean, obviously, you pick an atheist textbook, you got to deal with all the atheist stuff. But we also have problems, of course, if we have to rely on the Calvinists for their textbooks. So, a lofty goal, but we should write our own Lutheran classical textbooks. And finally, if you're looking for like a practical, how do I actually write a lesson plan? How do I implement it in my classroom? I strongly recommend using John Milton Gregory's 7 Laws of Teaching. He wrote it for Sunday school teachers. I use it in developing my courses and my lessons plans for engineering courses in undergrad. It is, it's great as far as a practical how-to guide in terms of thinking. So those are my parting thoughts that I came up with as listening to some of these other things throughout the conference, and then I heard someone else give book recommendations, so I want to tell you what I used in reference here. If you're interested in the medieval quadrivium, Institutions of Divine and Secular Learning by Cassiodorus, if you can find a translation of that. The copy I have belongs to my mother, so I can't lend it to you. Sorry, ask her. On Christian mathematical pedagogy, this is generically Christian, of course not Lutheran, but Mathematics is God Silent by James Nichol, the chapter 8 on pedagogy and resources is very good and very useful. I recommend reading that. And if you just want, again, more on how to do scope and sequence for a lower level, Samuel Blumenfeld's How to Tutor. Part 4 is on arithmetic. I think it's a helpful guide for us. Now, those are not theological recommendations. Those are just helpful tools that I've come across. And with that, I conclude my presentation and be happy to take any questions. Oh, man. No, I'm just kidding. All right, go ahead, please.
One thing, it's a little bit more of a comment than a question.
Okay.
But I noticed when you were speaking about Cassiodorus, you talked about how
Absolutely. I think that's spot on. I mean, if you think about that outer dimension, it's like current engineering and science practices or something. Science engineering practices is what it was called. It was like that outer ring of their figure. If we followed that pedagogy 200 years ago, engineers today would be learning the caloric theory of energy, which is not true, right? Because it's teaching, this is the practice of today. Well, that's okay, all right, I guess that's practical, but that's not the end of the education. You don't want people to only be able to do exactly what we've done so far, but we need to be able to develop our minds to investigate God's creation. Not for service of ourselves, like in the Tower of Babel, building monuments to ourselves and to mankind, but to service to our neighbor. And so, yeah, I would say it's definitely directly in opposition to STEM. I believe I saw another question in the back.
I was just wondering if you could go back to the chart you had.
Oh, sure, yeah. Feel free to add or critique. This was my opinion. Yes, sir.
What would you do with technology?
So, yes, technology must always be servant to the lesson. I don't actually think technology should really be much of a learning objective really anywhere in our curriculums. But there is absolutely use for it. In fact, Dr. Mildred talked about the use of graphing calculators in helping develop understanding of algebraic functions, right? And so the technology in our classroom is servant to this concept, this broader concept of algebraic functions. And the technology of today is a graphing calculator. Or if you're really rich and everybody's got a tablet, maybe the technology in your classroom is go access Wolfram Alpha, and they can do it on a computer. Or maybe the technology is let's go plug it into Excel. Right? So the technology itself is the tool, and we can choose to use which tools facilitate the lesson, because the lesson is what matters. And I had in my speech a nice closing line where I talked about how, which I didn't read, of course, but how our goal, we should always be placing the lesson first, not the student experience, right? What we're after is inculcating a lesson. We're not after giving them an authentic experience. Right? Did that sufficiently answer your question? Okay, yes, ma'am. Yeah, and let's focus on the and let's focus on the things that are truly beautiful. I mean, it's quite possible to use science and engineering to develop ugly structures, right? I mean, we can use it as a tool, so let's seek out to use it for good purposes, beautiful purposes. Sir.
You mentioned writing new textbooks.
Yeah, I know. Yeah, I know, right? If I was a good writer. No, I think it's worthwhile goal. And did you have a further question you wanted to say on that? Sorry.
Yes. So how would the textbook that you envision be substantially different from current textbooks?
Oh, right. So, as you get into, say, more and more like advanced math, like say my statics textbook, how do we make that classical, if you will, or like how do you do calculus as substantially different? It goes back to the foundation in the understanding that it is a language that we're developing. It's not a series of skills. And so that might manifest itself in how you write the book. And also, we might leverage what we have in terms of classical educational paradigms. And I know this is a Dorothy Sayers approach, but the whole like grammar, logic, rhetoric of a particular subject, we could do a classical approach to presenting the material because it is a good and useful way for students to learn. It's effective. in that regard. And quite frankly, some things are, I don't know, not particularly controversial, right? You don't have to reinvent the wheel. We just need to make sure that we start with the right foundation. It's more manifest in science, to be sure, because all the language throughout a book is going to have this evolutionary foundation, right? We're going to read about some mammal that has well-developed legs. Well, that's evolutionary language, unless you're talking about a specific specimen of the species, right? But it's not development, it was created, right? And so those are the challenges that you really run into science. When it comes to, say, calculus, I don't know if I have an answer for you. I'd have to really study some textbooks, I think. Yeah. Yes, sir.
You mentioned about the language of math and about how it can be used to give something the appearance of truth, just sort of by the facade of the numbers and about the, and not necessarily having the underlying conclusions being valid. I was wondering if you could comment about the similar sort of problems in both science and engineering, kind of in modern even scientific publications, where kind of the borrow phrase, you follow the science, begins to separate from an underlying truth to just this facade of truth.
Yep. No, I wholeheartedly agree with that. I think you misspoke though. You said follow the science. You meant to say follow the money, right? Is that what I heard? Right, no, so scientific inquiry, we have the problem of reproducibility in scientific literature, right? So I do my little analysis, I do my little model with my limited data set that I hold to myself because I got my funding for it. And no one else in the world could reproduce those results because, well, I don't know why, right? It's a problem, but it appears to be presenting truth. It appears to be advancing the body of knowledge when really what it is a way to earn money for research campuses, basically. And to put it in a negative, pejorative way, right? Okay.
Do you think actual, scientific astronomy has a place in this model?
Yes, I do, but I would put it in the natural philosophy realm, right? I don't think we should literally take the historic definition of astronomy and use that as what we mean in the Quadrivium, because what we're interested in is the broader language of mathematics, and I think the language of math and space and time is what that really represents. But we should, of course, we should study astronomy, but who's to say knowing whether there are 9 planets or 8 planets is fundamental or foundational to a quadrivial education. Oh, actually, I think we actually have till 3:15. Did I talk really fast? So if you have further questions, I'm happy to take more. Yes, sir.
On the topic of astronomy, you mentioned how students nowadays very often are calculator dependent.
Yes.
You work at an aeronautical university.
Yes.
Can anyone nowadays actually chart the course of the planets like the Babylonians could? Or have we forgotten?
I don't know. I teach mechanical engineering, so I don't look at the stars. We certainly don't spend time doing it. I mean, we use calculus and there's space physics and courses like that have been infested by a lot of humanistic ideologies in themselves. If you think of like Carl Sagan, I mean, that's where that might be manifest in a STEM university. But certainly, the particular mental processes used in that science, it would be difficult to identify, particularly because the notation in the language has changed so much for how we do that. Yes, sir. No, that's a great question, because California just published something where math now has the objective of promoting social justice, right? In lieu of teaching 2 + 2 is 4, I suppose, or in competition with. So when you get to engineering, it's more absolute, you might say, but what I get a whole lot of, particularly in the classes I teach, is climate change. That is baked into students, all of them. They've had it nonstop since the beginning. And so they come in with basically a belief in anthropogenic climate change. It's not founded on anything. It's just been inculcated into them and beaten. They've been beaten over the brow with it for, by the time I see them, 15 years maybe. And so some of that's more of a challenge that we face. So it's this rotten foundation that I see as opposed to the technical mechanics of math. We do, in the faculty lounge, gripe about how our students are good equation solvers, right? They've got a big kit bag of tools to solve equations, but they're terrible problem solvers. You can't present them an engineering scenario and they go identify the problem and determine the constraints and work through in a logical, sequential manner how to solve it, the steps necessary to solve it, and then present it. Engineers are notoriously bad communicators by reputation, right? It's terrible, it's true, and they're even worse when they're not taught a linear, progressive way to present an argument, a mathematical argument even. And so that's really where I see the problems manifest in engineering. I don't know if there's a hard line, right? How can you keep it out? There's no limiting principle without a Christian backstop, or foundation, rather. Right? So who knows how bad it will get. All right, well, if you have further questions, feel free to email me. I had my email up there. I'll put it up one more time. If you've got gripes or complaints with what I've said, feel free to email those as well. Thank you all for our time together.